My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I'd like to welcome you all to our International Physics webinar. So, good evening to all. Today it's our 86th International Physics webinar. Hope you are well and safe from Corona pandemic. So, I think you are, you have come to know that we have successfully organized we have organized 85th International Physics webinar, and in those physics webinar, physicists from different countries are coming as a main speaker. They are delivering their knowledge with our student. I think by this way, our students are benefited. So all we know that we are staying in a corona pandemic situation. We cannot continue our normal academic program inside the campus. So we have to start online program. So we are trying to adjust with this new normal situation. Today is very important day for our department. Today I'd like to welcome you all to a joint session between the Department of Physics, Pabna University of Science and Technology, and the Indian Institute of Astrophysics, India in Astrophysics. So we have with us here today Dr. Jayant Murthy sir, Senior Professor, Indian Institute of Astrophysics, India, connecting with us from India, and he has already connected with us. So I'd like to welcome our speaker. So good evening, sir, and welcome to our International Physics webinar. Welcome to our university through online, sir. And thanks for accepting our invitation.
My pleasure.
So for those who are new, I think you have come to know that the title of our today's International Physics webinar is Space Astronomy, why people want to do astronomy from space. Our speaker is Jayant Murthy, Senior Professor, Indian Institute of Astrophysics, India, and he has already connected with us. So I'd like to welcome again our speaker. Sir, welcome, and it's your time. You can start your session, sir. And thanks again, sir, for accepting our invitation. I think by your lecture, our student will be benefited, and they maybe know about astrophysics details by your lecture. So thanks again. You can start your session, sir.
Thank you. So it's my pleasure to give the talk. It's the first time I've given a talk to in Bangladesh. And of course, being online makes it easy, but I do hope to come and visit sometime.
Of course, sir. We'll definitely invite you.
Yeah. So what I will talk about is space astronomy, and I'm at the Indian Institute of Astrophysics. And anyone who might have questions, please do ask at the end of the talk. And you can also feel free to email me or connect with me on Facebook. So what I'm going to be talking about is space astronomy, and what I thought I would start with before going into the astronomy part is just to talk a little bit about the history, because this is a field. Excuse me. This is a field that's very new. Astronomy itself. Excuse me again. Astronomy itself is one of the oldest areas of science. People have been studying astronomy for thousands of years, from the first time that people looked up and saw that this is the time to plant crops, or this is the time to harvest crops. But space astronomy is much more recent. And the science of space astronomy, or going into space, it really started with Tsiolkovsky in the late part of the 19th century, early 20th century. And Tsiolkovsky was really the person who first wrote down all the equations of how to go into space. Robert Goddard was an American rocket scientist. The Goddard Space Flight Center is named after him. And he pioneered the use of liquid fuel rockets. Now, what he did was he was a shy person. He didn't really like publicity. So he went off into a field and just launched rockets in the 1920s. After him came Wernher von Braun. And von Braun has a more complicated legacy. He was part of the German V2 program, where they launched rockets from Peenemünde. And the goal was this was at the end of World War II, near the end of World War II. And so the goal was to bomb London into submission. So he would, so so these V2 rockets, they were launched from Peenemünde. Near the end of the war, the Nazis, who of course were not very nice people, they didn't want the rocket technology to get into the hands of the Allies. And so they sent an SS death squad over to kill von Braun and his entire rocket team. Von Braun got a hold of this. He heard about this. And so he fled, and he and his team gave themselves up to the Americans. And the Americans captured a lot of V2 rockets. They took them back to the US and started launching them almost immediately. Von Braun himself always said that he didn't know about the Jewish slave labor at Peenemünde. Now, with modern evidence, perhaps his conscience is not so clear. Still, he came to be part of the American space program. They stuck him in Huntsville, Alabama, at what is now the Marshall Space Flight Center. And they told him, you go ahead, work on your rocket technology, but we won't put you on TV. Because this was just a few years after World War II. And so they just didn't want these Germans with the sinister accents on TV. This is a much later picture of him at NASA headquarters in Washington, D.C. So he's standing at his desk with all the NASA rockets behind him. His counterparts on the Soviet side is Sergei Korolyov. And Korolyov, he had quite a hard life. He was caught up in Stalin's Great Purges and sent off to Siberia. Where by the time he was repatriated from Siberia, his wife had left him, his health was ruined. But he came back and he was the head of the Russian space program, the Soviet space program. And he was only known as the great designer. This was the height of the Cold War. The Russians were afraid that the Americans would send a death squad over to assassinate him. And so they never let his name out. They only called him the great designer. It was only after the breakup of the Soviet Union and the release of the papers that Korolyov's name became known. So now, in a very real sense, Korolyov is much better known than he was during his own lifetime. So the first space experiment, the first satellite, was Sputnik, October 4th, 1957. And so this was when the space era began. And all Sputnik did, it was a football-sized object. All it did was it went around the world over and over again, and all it did was it beeped. But this beep could be heard by anyone with a ham radio. So people heard it all over the world. And there were two reactions. One reaction were by people who were very excited. People like Homer Hickam, who wrote the book October Sky, and it was made a movie. So Homer Hickam, he was excited by this satellite that was going overhead. He immediately turned to rocketry. In those days, this was 1957. There weren't any of these nice rocket model rocket kits. So he built his own rockets out of Coke cans, filled it with things like nitroglycerin, and they were lucky they didn't blow up their fingers and lose fingers and eyes and things. But nevertheless, he shot off rockets. And so excited by this that he became part of NASA. And he was one of the first engineers to join NASA. So a whole generation of people who were excited by Sputnik. And the second group of people were the military, because once the Russians launched a satellite, what is a satellite? It's just a bomb that goes all the way around the world. So this was the 50s, the height of the Cold War. So they were worried that that the Russians, if they can launch a rocket and hit anywhere and go all the way around, they could just as easily launch a rocket and hit any location in the US. So no major city in the US would have been safe. So this guy here is Bert the Turtle. And he was part of this public movie put out by whatever the equivalent of HHS, this Homeland Services was at the time. And so Bert was lucky because he had his own turtle, he had his own shell. And so anytime there was an explosion, he could just duck and cover inside his shell. So what these people were saying was that anyone who was caught out in a nuclear explosion could duck and cover wherever they were. So they told school children to cover under their desk. If you were out in the open, you could cover in a doorway and cover yourself with a newspaper. Of course, all of these are silly. If there's a nuclear explosion, you're dead anyway. But still, this was the Cold War. So because it was the Cold War, it was a real big deal. And front page of the New York Times. And let me go to this a little later. So as front page news, everyone, it became a race between the free world and the Soviet bloc. So that was what the Cold War was. There was the free world, quote unquote, the Americans, the Europeans, the British, and then there was the Soviet bloc, the Poland, Yugoslavia, the Soviet Union, and so on. And it was a competition for who would show themselves to be superior. And so there was this idea that whoever would go into space first could show that their system was superior. It was a competition in everything. And so when the Soviets fired Sputnik, it was a big blow to the American idea that we're better in everything. So they immediately put a lot of money into space research, into space science and space research. And so the first thing they tried to do was to launch a rocket. And so here's a short video. I hope it plays okay.
During 1958, a large segment of the nation's scientists, engineers, and production experts was drawn together and given direction. Against this background, the country carried out a series of space experiments that yielded valuable data to the world's store of scientific knowledge. There were a number of failures during the year, and the United States promptly announced them. The first and most spectacular of these was Vanguard at the end of 1957. There were other Vanguard failures.
So you see what happened. Normally rockets are supposed to go up. This rocket actually went back down. And so the press had a field day with this. They would call it a flopnik, no goodnik, and so on. And so the Americans didn't have a working rocket. So because they wanted the first American satellite to be a fully American satellite, they wanted the US military to do it. And so they'd given it to the Navy. And this was the Vanguard program. The Navy failed 2-3 times, and the Americans just couldn't wait any longer. So they finally went to Werner von Braun. You remember they had put him in Huntsville, Alabama. And they said, okay, look, the Navy is failing, so you go ahead and see what you can do. And so the first American satellite was Explorer 1, which was launched in January of 1958. And already this satellite carried a space experiment. It carried a Geiger counter. And when they went up into space, that Geiger counter suddenly showed an increase in radiation. And so this was the Van Allen belts. The young scientist, James Van Allen, the Geiger counter was his experiment. And so his experiment was on the satellite. They launched it. And because he was the one who discovered the Van Allen belts, it's called the Van Allen belts. Sputnik had an experiment on board, but due to a variety of reasons, which I won't get into, it just didn't work. So the first science from space was done with this, or the first science from a satellite was done already by Explorer 1 in 1958. So then the Americans they wanted to show that they were still better. So they went on and the Russians did everything first. Yuri Gagarin was the first man in space. Laika was the first animal in space. Valentina Tereshkova was the first woman in space. Everything was done first by the Russians. So JFK, John F. Kennedy, he said, look, we have to do something first. We have to have a national goal. And what we will do is before the end of the decade, he said this in 1961, before the end of the decade, we will land a man on the moon and bring him back. I say very specifically a man on the moon and bring him back. This was the 1960s. It was a very sexist time, and there were no women astronauts. Valentina Tereshkova, yes, the first woman in space, but she was also the last woman in space until Sally Ride in the 1980s. Just a time when women were not allowed in space. And if I may, as a side note, I was very disappointed when ISRO did not put a woman in their astronaut corps. This is 2020. Very easily, they could have said, we will have a woman, at least on the first group of astronauts to be in the Gaganyaan program. But be that as it may, the Apollo program was a major program. Started out with the Mercury spacecraft. First American in space was Alan Shepard. Then the two-person Gemini program, which had Neil Armstrong. And then finally, the three-person Apollo program. And so these are Anders Borman and Jim Lovell, whom you may remember as the later commander of Apollo 13. If you haven't seen that movie, please do go watch it. It's an excellent movie with Tom Hanks as Jim Lovell and Ron Howard as the director. And the Apollo 8 in 1968, the three astronauts were the Time Men of the Year. They were the first people to go around the far side of the moon. And then in the next year, and they took this canonical picture of the space age. This is Earthrise as they come around from the far side of the moon. This picture later became a hallmark of the ecological movement. Rachel Carson in the early 60s had written A Silent Spring. And so what this picture showed is that you have the moon, the magnificent desolation, as Buzz Aldrin would later call it. But you can't live on the moon. All we can live on is the Earth. And when you look at the Earth from space, you see how isolated it is. We're one small world in a vast darkness of space. And from space, you can't see any borders. You can't see any differences between people, no religions. We're all one people. We're on one planet. And it's our duty to look after the planet we live on. We haven't done such a great job of it now with climate change and wars and all this. But nevertheless, this is where we live. So the first part of the space age ended with Apollo 11. This is actually Buzz Aldrin on the moon. There are very few pictures, if any, pictures of Neil Armstrong on the moon, because Buzz Aldrin liked to have his pictures taken, and Neil Armstrong was not so anxious to have his pictures taken. But anyway, so Neil Armstrong was the first man on the moon. One small step for a man, one giant leap for mankind. And you always get questions about was the moon landings faked and so on. So I never answer such questions, mainly because there's so much good science to focus on. Why worry about the bad science? But there are people who have gone in and countered all these conspiracy theorist guys. So for those who are interested, do go to badastronomy.com and you'll see a whole list of things. The one thing I was actually interested in was why the flag looks like it's waving. And this is the first thing the conspiracy theory guys say. If the flag looks like it's waving, you must have air. So clearly it was done in Area 51. But you have two different pictures. Again, this is Buzz Aldrin. In one picture, he's saluting the flag. In the other picture, he has his hand down by his side. And you see that the astronaut moves between the two pictures. The landscape moves, but the flag doesn't. Same wrinkles. And the reason this happened is because one of the springs broke. So the flag did not extend out all the way. NASA liked this, and so because they liked it, because flags should look like they're waving, so on all future missions, they deliberately did not extend the flag out all the way. So of the Apollo program was not a science mission. There was no astronomy there. The only scientist on any of the Apollo missions was on the last one, on Apollo 17, Harrison Schmitt, a trained geologist. And many of the moon rocks that were brought back on Apollo 17. So that was purely a political mission. The reason was that we, meaning the free world, wanted to show that we're better than the bad guys, meaning the Soviet Union. And so they sent a man to the moon. So purely political. Once they did that, there was not much interest in sending people to the moon again. And so we haven't sent anyone to the moon since the 70s. I think there's 3 or 4 people left alive from all the astronauts who went to the moon. So another reason to go into space is because of things like weather forecasting. So there's a lot of money to be made from this sort of stuff. Here is 4 cyclones off of the eastern coast of India, I guess off the eastern coast of Bangladesh. And so clearly we want to know when cyclones are coming. We need to know the bad weather. So one of the benefits of space, weather forecasting. One of these houses is mine. I won't tell you which one. So remote sensing. From space, we can see if there's rice usage. We can see what the forest cover is. We can see if we can look and see where the fish are. So all these benefits of space, remote sensing, weather forecasting, military applications I won't even talk about. Everyone uses GPS. Many people have a smartphone. That smartphone, how do you call an Uber or an Ola or whatever taxi service? How do you know where you are? Well, that's because of GPS. GPS wouldn't work if it weren't for satellites. Incidentally, GPS units are one of the best applications of basic science, one of the best arguments for basic science. If it weren't for Einstein in 1905 and 1912 with special relativity and general relativity, we would not have we would not be able to use GPS satellites, because GPS satellites, you have to correct both for special relativity because of the motion of the satellite and for general relativity because of the gravitational difference between the satellite orbit and the Earth. So every time you use GPS on your phone, you're testing both special and general relativity. Global telecommunications used to be important, and the Earth was for a while one of the brightest, perhaps brighter than the sun in radio waves. Now, as we've gone to fiber optic because of the dot-com boom, we've gone heavily into fiber optic. Now, a lot of our traffic is carried by fiber optics, and so we don't actually radiate as much into space. But still, many people do get satellite TV, satellite TV. So all of these things that I've talked about are commercial applications of space or political applications of space. They're not astronomy. They're not science. So why do we do space astronomy? Before we can answer that, we have to ask an even more basic question. Why do we do science at all? And so the standard answers are because, as I said, with general relativity or with the GPS unit, the basic science of today is our technology of tomorrow. Lasers, basic science out of Bell Labs, and now you use lasers in every aspect of your life. So that's the standard argument. But I'd like to go a little deeper, even more than just saying that we do science because it'll help us tomorrow. I think we do science because science is important in itself. It's important because we're curious about science. It's important because it teaches us about rationality. Why does science work? If I drop a ball, the ball will fall. It won't fall. The sun will rise tomorrow, regardless of how much I pray to the sun. I may pray to the sun, don't rise, it'll still rise. It rises not because of me, it rises not because of any prayers we do, but it rises because of science. And so science is a cause effect. There's a cause, there's an effect. And I think it's very important for us all, no matter what we do in life, to have this basic rationality. Once you say science is important, then of course that justifies anything. Why astronomy? Astronomy is important because we want to know more about the universe. We want to know how the universe works. It's a bonus that astronomy has some of the best looking pictures in space. I mean, in all of science. And astronomy is one of the easiest things to understand in all of science. But my bottom line is that I think it's important that we do curiosity-driven research. And I'll leave it to everyone to come up with their own justifications for that. Now, space is another kettle of fish. Why are we going into space? Space is very expensive. Every time you go up, you have to have a big rocket. And that rocket has to have all this fuel, so you carry a lot of fuel. 90% of the weight is just the fuel. And once you do that, you dispose of that fuel, you dispose of your first stage, your second stage, and finally you send a very small payload up into space. Even a big payload is maybe a ton. And so it's just expensive. Then once you send it up, it has a limited lifetime. You can't fix it. The Hubble Space Telescope was the one exception, but it's the exception that proves the rule. Every time they went up to fix it, it was like sending up a whole new mission. So because you can't fix it, there's no room for mistakes. And mistakes happen in space. The classic example is the Mars Observer, where one group of people were sending updates in foot-pounds. The other group of people were applying the updates in Newton meters. And so finally, the deviations just got so bad that they lost the spacecraft. There was another spacecraft where after the spacecraft launched, this was a student-built satellite. After the satellite launched, they found that it pointed away from the sun. The solar panels pointed away from the sun. And so it lost power. Why did it point away from the sun? It's because instead of a +1, someone put a -1. So these little mistakes happen, and because they happen, you lose that complete mission, along with however much you spent. Maybe $1 billion in the case of the Hubble Space Telescope, maybe $500 million, maybe $5 billion. The JWST, maybe $15 billion. So a lot of money. So why do we want to go into space? The most basic reason is because of our atmosphere. In many ways, the atmosphere only allows through specific wavelengths. So it will allow through visible light, the light that we see in, from blue to red. So we can look up at the sky and we see colors from space. It allows it allows the radio, so we can look up and we have these big radio telescopes like GMRT in Pune. But my own field, the ultraviolet, you have to go above the ozone layer. So you have to go up to an altitude of 200 kilometers or so. There's all sorts of bands in the infrared or microwave where you have to go above the water. So maybe if you're in a high-flying airplane or a high mountain, maybe you can manage to do some infrared astronomy or microwave astronomy. But for much of the wavelength, X-rays, gamma rays, UV, you need to go above the atmosphere. So that's 200 kilometers or higher. Now, this wouldn't matter if the UV sky looked like the visible sky, but when we look at different wavelengths, what we're really looking at is different temperatures. Because as you go from the shortest wavelengths, gamma rays, you're looking at the highest energy. Energy is nothing but temperature. So you're looking at the highest temperature, highest energy parts of the universe in the gamma rays. When you go to the radio, the other end of the spectrum, you're looking at the coldest areas of the longest wavelength, lowest energy, coldest parts of the universe. And so when you're looking in different wavelengths, what you're really looking at is the temperature of the universe. And here's a picture of the central disk of our galaxy. So when you look in the radio on top, when you look in the radio at the top, you're looking at cold molecular gas, temperatures of 10, 20 degrees Kelvin. As you go down this plot, you pass the optical, which is things like stars like our sun. So these are stars with temperatures of 5,000 or 6,000 degrees. You can see these dark patches in the Milky Way, in the disk of the galaxy. That's caused by interstellar dust. You can see this interstellar dust in the infrared. It blocks the light from the visible in the optical, and then it re-radiates that at a temperature of 20 or 30 or 60 degrees in the infrared. And then finally, as you go to the very shortest wavelengths, X-rays and gamma rays, you start to see single objects. So these are black hole candidates. So that's one thing, that we can't see a lot of the universe from the ground. Then the next thing is that the sky is bright. From major cities, such as where I am in Bangalore, you're lucky to see 1,000 stars in the sky, maybe even 100 stars in the sky. If you go out to remote areas where the sky is dark, you just won't recognize the sky because there's so many stars, so many more stars than you're used to. But even in the darkest areas of the Earth, the mountains in Chile, the sky brightness is 1/23rd magnitude star per square arc second. This sounds very faint. We can see down to about 6th magnitude. So this is maybe 1,000,000 times fainter than we can see. But the thing is that when you're looking at the darkest parts of the sky, something like the Hubble Deep Field or the Hubble Ultra Deep Field, you want to get down to 30 magnitudes per square arc second. So this is 10,000 times fainter than you can see from the faintest region on the Earth. And so here I'm showing a picture of Orion, just taken from the space station. And you can see from the International Space Station, here on the top of the picture is Orion from outside the Earth's atmosphere. At the bottom of the picture is Orion from within the Earth's atmosphere. And so you can see how bright the Earth's atmosphere is, even from space, compared to really looking out in space. And then finally, again, because of the atmosphere, we all know that stars twinkle. So why do stars twinkle? It's because as we look at the star through the atmosphere, we're looking through a number of different cells, microcells. And each of these microcells will have some turbulence. So the temperature will fluctuate and the index of refraction will fluctuate. So as you look at the star, you're looking through a constantly changing index of refraction, which causes the star to change a little in position and brightness. So that's why stars twinkle. Planets don't twinkle because they're large enough that the twinkling is entirely within the disk of the planet. So the net result is that we can't look at better than about 1 arc second in the sky. So don't really worry about the details. Don't worry about 1 arc second is. But here's the practical effect. Here's a picture. Here's a photograph of this galaxy, the NGC 4314 from the McDonald Observatory. And the central square is you can see that the central square is nothing but a blob. You can't see any detail at all. But yet, when I look at that central square through the Hubble Space Telescope, I see that now I have the central bulge of the galaxy surrounded by this disk of star formation. So these are all young stars. These are stars which have been born within the last few million years. And I just can't see it in the visible or from the ground because of the atmosphere. So why do I want to go into space? It's because I see these new wavelength regions. I have freedom from city lights and no twinkling. Now, the first space experiments were done with sounding rockets. And so, as I told you, the Americans captured all these V2 rockets. And so when they captured the V2 rockets, they immediately started using them for science, for astronomy. And they launched them, and they took the first UV picture of the sun. They captured UV pictures of stars, X-ray pictures of stars. So they did a lot of science from sounding rockets. But finally, what happens is that a sounding rocket goes up and comes back down. And so your payload is quite small, only a few kg, and you're up in space for only about 20 minutes or so. So you have a small payload and you only get about 20 minutes of observation. So there's only a limited amount of science that you can do. It's great for quick results. So if a comet is coming, very often I can't build a spacecraft to look at that comet. So what I can do is I can launch a rocket and take some quick data of that comet. And it's also very good for training students, because a major science experiment can take anything up to 10, 15, 20 years, whereas a sounding rocket can be done in a few years. So within a 5-year lifetime of a student, that student might get to participate in 2 sounding rockets, and for a cost of maybe a couple of $1 million instead of a cost of $100 or $500 million for a satellite. And so it's a good training ground for students to learn how to work with space data. So in the last 10 minutes or so of my talk, 10 or 15 minutes, what I'll do is I'll talk about some of the outstanding science that has come from these space astronomy experiments. So most of the science has come from NASA. So you can go to this website, science.hq.nasa.gov, and just look at a list of the different NASA missions. And one of the great things about NASA is that they realized in about 2000, maybe a little bit earlier, maybe 1990, that they had to market themselves better to the public. So they found that their workforce was aging, fewer people were going into science. Many of the people in science had gone in NASA had gone in with Sputnik, but those people were retiring and new people were not going in. So what they said was that every space experiment had to have an outreach program aimed at K to 12, kindergarten to 12 and beyond. The second thing they did was they said that all NASA data has to be released to the public, hopefully immediately, but if not immediately, after a short proprietary period, maybe 6 months, maybe 1 year. And so you can go to this website, and from any of these missions, you can download the data and play with it yourself. One way to do amateur astronomy is to get a telescope and look up at the sky. In Bangalore, that may not be such a great thing. But another way to do amateur astronomy is just to download data from big missions and just see what they show you. So I've only focused on a handful of science results. Do go to the website, do look through and see how much more science there is. So one of the more outstanding results, which resulted in 2 Nobel Prizes, or rather 1 Nobel Prize shared amongst 2 people, was the discovery of, not the discovery, but rather the measurement of the microwave background. This microwave background was first discovered by Penzias and Wilson from radio observations in the late 60s. And but there was always some question about whether this radiation was truly from the Big Bang or not. So what NASA did is that they launched this mission called COBE, Cosmic Orbiting Background Explorer. And it was designed to look at this background from the universe. And what they discovered is that the background from the universe is a black body. Don't worry about what a black body is. Basically, a black body is a unique spectrum that defines the temperature. So they found that the spectrum of the universe was that of a black body with a temperature of 2.7 degrees Kelvin. That is, the universe has a temperature of 2.7 degrees. And so this got a Nobel Prize. Another part of that Nobel Prize came from showing that this looked the same in every direction. The universe is isotropic and homogeneous. The only way this can be is if there's a Big Bang. If the universe started from a single point and expanded. The universe had a specific starting point. It was not around forever. The second thing I'll show is the Eagle Nebula. And so what these are is one of the most famous Hubble pictures from the Wide Field and Planetary Camera. And so what these are molecular clouds, projections of these molecular clouds. And what I want to highlight here, these molecular clouds contain lots of gas and dust. And so what I want to highlight are these supposedly red stars in these embedded in these molecular clouds. These are not actually red stars. These are blue stars. They're very hot blue stars. And so these are stars that have just been formed. By just, I mean in astronomical timescales. That means within the last few million years. Just been formed. The reason they look red is because we're looking at them through all of that dust. And so in much the same way that the sun looks red near the horizon, these stars look red because we're looking at it through all of this dust. The dust preferentially scatters the blue radiation, and so the shorter wavelength radiation, and so the stars look red. So what are these? These are molecular clouds, yes, but these are also sites where stars are being born. So these are stellar nurseries. Now, this is from another of the Space Telescope instruments. This is the STIS, the Space Telescope Imaging Spectrograph. And what they did is that they put a spectrograph, and I'll explain that, across the center of this galaxy, M84. And so when we look up at the top here, we're seeing light that's neither red shifted nor blue shifted. That's what a spectrograph will do. It will tell you if the light is red shifted or blue shifted. So when you're looking far from the center of the galaxy, the light is neither red shifted nor blue shifted. As you get closer and closer to the center of the galaxy, now suddenly the light is heavily blue shifted. So what does it mean when the light is blue shifted? That means that the stars are coming towards us very fast. It's a similar phenomenon to when an ambulance is coming towards us fast. The sound is shifted to higher frequencies. So here, the light is shifted to higher frequencies. That is, it's shifted into the blue. From the magnitude of this shift, we can tell how fast these stars are moving. As you cross the center of this galaxy, now the stars are moving away from us very fast. And again, from the magnitude of this, you can tell how fast the stars are moving. So what this tells us is that the stars are moving around this point right here. We can tell the mass by how fast these stars are moving. We know how much mass, we know what the volume is here. So the only way you can have that much mass in that small a volume is if there's a black hole there. So what we're seeing is a black hole at the center of M84. And here is the black hole at the center of this galaxy. And these observations are got what 2 parts of the Nobel Prize this year came from these observations. So if you see this star here, not that star, this star here, it whips around that center of the galaxy. It whips around the black hole, whips around this point right here, which is where the black hole is. And so this is just like a comet in our own solar system. It starts out far away, it moves slowly. As it comes closer and closer, it speeds up and then whips around. So this is just Kepler's law. That's all it is. Kepler's law in our solar system, it's where we see Kepler's law in the orbit of the planets, in the orbit of the orbit of comets. Here in the Milky Way, we're seeing it in the orbit of the star. So this is what a black hole is. And this, although these were ground-based observations, not space-based observations. So that earlier picture of this spectrograph, that basically shows exactly the same thing. The stars are orbiting the center of the galaxy. There's a black hole at the center of every galaxy. You may be hearing a lot of results from Gaia now. Gaia is just releasing more and more data, and it's a wonderful experiment that measures the distances to stars. You wouldn't think that's very sexy. Why do we care about the distances to stars? But really, this allows us measuring the distances to stars, explicitly measuring the distances to stars, allows us to measure the distances to everything in the universe. And so Gaia, with its precision distance, with its precision astrometry, measuring, telling us exactly where stars are, opens up a wide variety of science, a large number of science results. So I'm not going to go into it in detail. I don't have time, but do look at some of the Gaia results. We're seeing some of it in the popular press, but you can see more and more if you look at any part of the science literature. It's revolutionizing the way we understand our galaxy and by extension, other galaxies. Here's an experiment. LISA has not flown yet, but Ligo, the ground-based counterpart, got the Nobel Prize 2 years ago. So the Nobel Prize for 3 years running has gone to astronomy. We're quite proud of this. And what LISA is 3 spacecraft. Ligo is on the ground, and the way they do it is that they have very precise pendulums that measure if a gravitational wave goes by. But on the ground, you're subject to all sorts of shocks. You have seismic waves, you have North Korea nuclear weapon tests, all these trucks going by on highways, all this noise that you have to worry about. But if you go out into space, you can now have what LISA does is that they have 3 spacecraft where the distance between the 3 spacecraft is measured very precisely. And anytime a gravitational wave goes by, it'll change the distance between these spacecraft, and so they can measure these gravitational waves. So LIGO measures one frequency, and they're sensitive to these black holes. They discovered this neutron star, but they're sensitive to one specific class of objects. LISA will be sensitive to much more. It will open up the field of gravitational astronomy. The Global Surveyor, because I wanted to show one planetary mission, this is two images of the same area of space of Mars. This one is August 1999. This one is September 2005. And what you can see is a bright streak here. And this is water ice. So it's ice on Mars, not ice that's hundreds of millions of years old, but ice that's in the present day. So it's ice it's water that's actually on Mars right now. And you must be seeing all of the Mars results that are coming out. So finally, let me show something about which there's a lot of excitement now, which is finding exoplanets. Why? Because if you find exoplanets, maybe you can find life on other planets. And so you may have heard just a few days ago, they found a large number of terrestrial planets, planets that look like the Earth. So now, how does this work? Well, when the planet goes in front of the star, then it will cause a small diminution in the light. It's like a lunar eclipse. The moon blocks the whole of the sun for us. This planet will block a very small fraction of the star. So if you're looking at the star at the right time and in the right inclination, you will see a small drop in light. And this is what the Kepler mission did. Kepler went up, and it looked at a number. It looked at all these systems in one small area of the sky, and it found that almost every planet, every star had a planet. When I was in graduate school, the only solar system that we knew was our own solar system, where it was quite simple. We understood everything. Now we look out and we see that our solar system is the exception. Other solar systems are looking so different. The many systems with hot Jupiters orbiting where closer to their star than Mercury is. We find systems with multiple stars. There's one system which they call Tatooine, which has 2 suns. So a whole variety of systems. And this has caused a revolution in exoplanet science. And so let me end with one last slide, which is just to get back to a point that I made earlier, which is that now we're in the middle of a paradigm shift in astronomy. Earlier, astronomy was done by individuals. It was done by one person at a time. They would sit in their lab with their photographic film and take photographs, and then they would observe and do one object, one thing. But now what has happened is that we have much larger detectors, we have more expensive instruments, especially now that we've gone to space. And so now there's an understanding that we can't be selfish about our data. The data that we get should really belong to everyone. It's the property of the public, not of the observer. The taxpayer paid for the data. The taxpayer should own the data. And that goes along with faster computers, with internet access getting faster. 20 years ago, there's no way I could have given a lecture like this over the internet. And scientific results are now publicly accessible. Almost every paper in astronomy is published free. Anyone can go and they can look at the paper, they can read the paper. Many people know Stephen Hawking through A Brief History of Time. But that's not the work that Hawking did. The work that Hawking did is really in his scientific papers. And now you can go and look not just at what he wrote to the public, but you can go and look at the actual science that he did. And so now astronomy research can be done at home, and perhaps more practically, it can be done in universities and colleges throughout Bangladesh and throughout India. So let me end there, and I'm happy to take any questions.
Thank you, sir, for your nice presentation, sir. We have got some questions, sir. So if you allow, we can start our discussion session, sir. Can we start the discussion?
Yes, please.
So the first question, why can't we
live on the moon? Oh, well, I mean, the obvious answer is because there's no air and water there. But I assume you mean, why can't we live on the moon? Why can't we build cities on the moon? So, of course, that's everyone's goal. And why stop at the moon?
Yeah.
Elon Musk wants to go to Mars. But really, if you look at it, you can build a base on the moon. You can put a base on the moon where some number of people can live. 3 people, 10 people, 100 people. But you can't build a city on the moon. To send 1 million people to the moon or 1 million people to Mars, it's just that expenditure of money is just so much. We just can't do it. And you have other practical reasons too that I won't talk about. You have radiation, so both radiation from the sun and radiation from space. So let's say we want to go to Mars. It's just hard to go there because you have to be protected from the radiation to go to Mars. So that's a practical reason, at least with the technology we have now.
Thank you, sir. Yeah, we have another question. So, in which book it is written that Neil Armstrong landed on moon?
Yes. What about Neil Armstrong?
So, in which book it is written that Neil Armstrong
Which book is it
landed on
written?
moon?
Oh, I don't know. I watched it.
Yeah, yeah.
I was 8 years old when Neil Armstrong landed on the moon, and so I watched it. So I mean, I don't know what you mean. What book was it written? I saw it, and so did I don't know how many billion people over the world.
So we have another question. So why our moon landing Chandrayaan was a failure? So detailed technical analysis, please. Maybe Indian Chandrayaan
Yeah,
failed. So they
I
maybe
haven't seen much of the report. I understand it was some sort of software problem, but space is difficult. So it's a big thing to even go that close to the moon. It's okay. We didn't make it that last step. Neither did that Israeli spacecraft Beresheet, but getting that far is valuable in itself.
so we have another question. So where does the space actually
Yeah, so
begin?
that depends on what you define as space. Many of these people want to call it this, what is it called? The von Karman line, I think. That's something like 25 kilometers. So that's when our atmosphere goes down to some whatever low level. So if you're looking at many of these space tourism guys like Virgin Galactic, they'll take you up for, I think, $100,000. They'll take you up to some 25 kilometers or so and then bring you back down. And then you can call yourself an astronaut. But to me, space really, you need to be at least in low Earth orbit. You need to be orbiting. So maybe 300, 400, 500 kilometers.
Sir, thank you, sir. We have another question. So there is a news that ISRO will launch its Venus mission in 2025. So what will be the main target areas of?
Yeah, that I think that mission is may go under some changes. I understand there's an American experiment that's going on it. So what they're I don't know what the latest is on that spacecraft. What is it called? The Shukriyan or some? Anyway, whatever the latest is. When I saw it last, what they had talked about was that they wanted to send a drone in and measure the conditions in the atmosphere. So really, I don't think they were planning to go all the way down to the surface. I think they were planning to measure the conditions in the atmosphere. But really, I don't know much about it.
Thank you, sir. We have another question. So how long do stars live and how
Yeah,
do
so this
stars
depends
die?
on the star. So you have the
Life.
smallest stars, which are these red stars that you see in the sky. And if I say that, when I say one solar mass, I mean the mass of our sun. So that's what we call, that's a standard unit, one solar mass. So if I say a star is maybe 1/10 of the mass of our sun, a tenth of a solar mass, those stars will live 10 to the 12, several times 10 to the 12 years. So the stars that are these cool stars have not died yet at all. Now, when they die, what will happen is that they'll eventually stop all fusion, and because they're so small, nothing more will happen. They'll have hydrogen fusion. Once the hydrogen fusion stops, there's no more fusion, and so the star will eventually cool and become a black dwarf. A star like our sun, it will go a little further. It'll have hydrogen fusion, then helium fusion, then perhaps up to lithium fusion. And so what will happen is it'll blow out its outer layers, and you'll be left with only the core of the sun, which will be a very hot white dwarf. That white dwarf will not have fusion because it's too small. And so eventually that will, again, cool down and become a black dwarf. And the sun will live maybe 5 billion years, 10 billion years. So we've lived about 5 billion years, maybe another 5 billion years more. If you look at the very hottest stars, stars that are 10 times as big as the sun, maybe 100, as big as 20, 30, the most massive stars, maybe 100 times as big as the sun, their lifetime will be much less, only a few million years, 5 million years. And these are the stars that will blow up as supernovae, and you may get neutron stars and black holes left as their final product.
Thank you, sir. We have another question, sir. Can you explain a bit on Van Allen belt?
The Earth has a magnetic field. And so because of the magnetic, the Earth has a magnetic field, the sun has lots of charged particles. And so what happens is that the charged particles come in from the sun, they hit the Earth, and because of the magnetic field of the Earth, they're redirected into these belts that go around the Earth. So really the Van Allen belts protect us from a lot of the solar radiation. It's trapped solar radiation. The aurora that you see is the end product of one of these Van Allen belts in the Earth's atmosphere. So that's all it is. It's charged particles from the sun being trapped in these in the Earth's magnetic field.
Thank you, sir. We have another question. This may be the last question. So how much is theoretical astronomy and astrophysics different from the observational astronomy?
It's a spectrum. We have there are very few pure observational astronomers. There are very few pure theoretical astronomers. So it's a broad spectrum. Most people do some, and some people do more observation, some people do more theory, but finally, astronomy is a data field. We have to have data, and we have to we have to put, we have to test our theories by looking at data. So it's hard to separate like that. If you ask, for instance, I would say I'm more of a data scientist or a space scientist. I work with space-based data. I build some instruments, but mostly I do space-based data. But I have to do modeling, I have to do observations, I have to do theory. So I do a little bit of everything. And most astronomers are some combination of this.
Yes, sir. We have another question. So has any black hole been found with a charge?
It's not clear how we would measure that. So I've also asked this question, and I've looked for the answer. But it seems that most people think that black holes are neutral, just because they're so large that they'll take protons, electrons, whatever you want. So probably they're neutral.
Thank you, sir, for your nice presentation and discussion, sir. I think by your presentation, students have learned a lot of things. So we would like to say thanks again on the behalf of the Department of Physics, Pabna University of Science and Technology, sir, for accepting our invitation. So it was a great webinar with you, sir. I think the students have learned a lot of things about astrophysics. And in near future, we'll arrange another webinar with you if you have time, sir. Thanks again.
Absolutely. Thank you for asking me.
Bye for today, sir. So bye for today,
Bye.
sir. Thanks. Yeah. Good night, sir.